So looking at the scatter plot, we do see that apparently we have a positive correlation between these two variables of height and weight of a person. And we might expect that too. Intuitively, we would think that someone who's taller is going to weigh more. But based off this data, the relationship does look a bit weak here. In fact, when we found the correlation coefficient, it was only 0.356. So what do you think? Do we think we have enough evidence based off of this to say that a positive correlation does in fact exist? Or do we see this just because of natural variability in a person's weight? So let's go ahead and go through the process that we can use to help us identify and answer this question. That's going to be our linear regression t-test. So in completing this test, we're going to do our 4 steps. Our first step is, of course, to write our hypotheses. So for step 1, we're going to be using a slope. So remember, beta represents the slope. It's like b, but the Greek version of it. And so this is the slope of the linear regression line. So of our relationship between the two variables, height and weight. And what do we know about this slope, or what are we assuming about this slope for our null hypothesis, is that if there is no relationship, basically we should see this as just being flat. That knowing the height tells us nothing about the weight. It doesn't tell us it's going higher or lower. So we're assuming that the slope is 0. But specifically here, we want to know, does a positive correlation exist? So we're going to use the one-sided alternative, where we're just trying to see, is that slope positive? Is it greater than 0? And so what's the method that we use? So well, step 2 is, this is again going to be just the linear regression t-test. So step 3 is what you're waiting for, is how do we perform this test using art of stat? The answer to that is actually in the same exact place where we were doing the regression lines to begin with. We're going to choose the linear regression on our art of stat menu. From here, we're going to enter in our own data. And again, what we're using here is for the x variable, we see that the height is being used to predict the y variable of weight. And hopefully you opened up the data set, but we can just copy and paste our height and weight from the variables here, which is wt is weight and ht is height. So let's start with the height. We'll put that into the x. And then we'll copy the weight and put that into the y. So now, when we look at this, it gives us the scatter plot as well as the information for building our linear regression equation. But with all these options here, you're going to see one that's going to be useful to us, and that is our p-values. So this option where it says show standard errors and p-values will add on to this, where now not only do we have the standard error of those, but we have the test statistic and the p-value. Now, which one are we interested in? Because it gives us both the intercept and the slope. We are interested in mainly the slope, right? Because that's what's telling us and defining our relationship. So here we have both the test statistic and the p-value. So we will copy that entire thing over. And so finally, since we have our results here, we can actually come up with our conclusion. So in this case, step 4 is our conclusion. What are we going to conclude? Since the p-value is less than, it didn't state the alpha, but I believe we're using 0.05, so we'll say less than 0.05. Again, this means that this is unusual to see this kind of slope here if there was really no relationship at all. So we're going to reject that null hypothesis of the no relationship. And of course, if we're rejecting the null, then we're concluding that a positive correlation doesn't exist. So we have sufficient evidence to show that a positive correlation exists between a person's height and weight. So before we end here, let's think about some of those reflections on, is it appropriate to use linear regression in this case? Were a few conditions that we presented earlier on, so let's just analyze those very briefly. So the first thing we want to know is this linear? So remember, linear can be useful for us. So Li, linear. What do we notice here? Just by looking at the scatter plot itself, do we see any curves? Not necessarily, but sometimes those curves are very hard to see in a scatter plot, and we might want to look at another type of plot instead called the residual plot. So going back to our regression output, you'll notice that on here we have show residuals on a plot. And we can see what those residuals are. Basically, it's finding that distance between our prediction, which is the line that we came up with, and each one of these values. But one thing about those residuals is if we analyze just the residuals, it's going to help us see if there's any curves. So when we go to the top with the residual analysis, rather than having the prediction line, it just looks at the residuals, and it makes it easier to see if there's any curves available. And I don't see any curving, at least nothing obvious within our residual plot. So in this case, I think it is safe to say it's linear. So I'll say it appears linear in the scatter plot and residual plot. So Li linear. Next we want to talk about normality. So remember, this is the normal distribution of residuals, right? The other thing that we know about our residuals is that they're errors in the sense of being an error from variation, from just random variability. And so we hope that if this is doing a good job predicting, then those errors in our prediction, that variability, is going to be normally distributed. So one way we can do that is in this same output, you'll see that there's a box that's listed as histogram or box plot of residuals. And when we click that, we get a nice box plot and histogram. And this helps us see, does it look approximately unimodal and symmetric? It's not going to be perfect. It might be even have a slight skew to it, but looking at both of these, it does look somewhat symmetric. So I think it's still appropriate. So in terms of this, we can actually just state the residuals appear mostly symmetric and unimodal, which is what we talk about when we're talking about the normal distribution. It should be symmetric and unimodal. Next, we have E, equal variances. So what is this one telling us is that the spread of our residuals should be even throughout. And so we shouldn't see any thickening or thinning of our residual plot. Now here, it does look like it actually does thin out or thicken out a little bit here. It's not super obvious, so I'm not going to be as concerned, but that may be something that may affect the results if we were to look at this. So there is a slight thickening. As we see, it's very close together, close to zero here, but here it's very spread apart. So that might be something worth noting. The variation, or variances, starts smaller on the left side, but widens on the right slightly. So that's just something to kind of note. And lastly, R could stand for randomness, but also randomness in our residuals. So everything we've been analyzing in this has been about the residuals and making sure that basically we have no patterns. And so everything we've been looking at is just making sure there's no specific patterns that could describe the error that we see. And even though being able to be linear or normal or, having equal variances are a good thing, just always look back and see, does it just look pretty random? And I see there's no real pattern to these residuals at all, and so it does look random. So I'll just say there is no noticeable pattern in our residual plots to worry about. And there we go. So this is one way that we can reflect and think back and think, do we satisfy these conditions for this linear regression test to be reliable.